Okay, so we have quite a bit to get through. I apologize. I'm a little slow on getting the lectures up. They'll all be up today. So if anyone needs to review. So we left off by leaving at the austenite prior austenite grain size, and we had mentioned that this is an important microstructural aspect because it largely governs the toughness of the steel in the hardened and tempered state. And this is largely because so many things take place at the grain boundaries, right? The nucleation of ferrite, of martensite, right, all takes place at the grain boundaries. And then in alloy steels, we have segregation of elements that to the grain boundaries in the austenite phase that weaken the interfaces, right? And when we transform either to martensite or then temper, right, these alloying elements tend to stay at the prior austenite grain boundaries and give us short circuit fracture paths. So basically, if we sort of go through the steps, right, we start with our original microstructure here, and this is a hypereutectoid microstructure. So we have a nice coarse perlite and proeutectoid ferrite that's formed. As we go up in temperature, we recrystallize and we get a very fine austenite grain structure, which will eventually grow and consume the proeutectoid ferrite. And if we continue to go up in temperature, we will get a very coarse austenite structure. Right. So this is our transformation temperature. So fine austenite grain, so very, very fine austenite grain, a fine austenite grain, coarse grain, and then if we increase temperature too much, we get very large austenite grains, which is typically called overheating. And the driving force for this is basically any other grain growth, right? We're reducing the energy of our system by consuming interfaces. Yeah.
So, if that's hypereutectoid, you're supposed to grow proeutectoid phenotype, right? That's
oh yeah. I'm sorry, hypoeutectoid, right? Because we've got proeutectoid ferrite go above. Yes, thank you for pointing that out. Remember, my propensity to make mistakes is infinite. So, right, and basically, we can sort of divide steels broadly into two classifications. One of those are inherently fine grain or inherently coarse grain in the austenite state, and the primary difference from these is just in the same as in aluminum, right? If we can have an alloy system that has lots of oxide, carbide, or nitride formers in it, then we can get a fine dispersion of these secondary phase particles, which will then pin the grain growth, right? If we are either too high or we're in a system that doesn't have sufficient formers for secondary phases, then those particles are going to dissolve and we won't have any resistance to grain growth, right? And this will sort of come back. We'll see as we go through some different materials how we get these different carbides. Okay. So we talked about the TTT diagram for carbon steels a lot, right, for just iron carbon. Once we have alloying elements in there, we basically have a couple different ways our TTT diagram can look, right? So our basic one is depending on the alloying mix, we can get a TTT diagram that looks very much like plain carbon steel, where we don't have the bainite region peeking out. The bainite would be back here on the TTT curve and is hidden by the far pushed forward nose of the pearlite region and a fairly high martensite start time, or martensite start temperature, right? And so, right, and then we have what are called the steels that exhibit the pearlitic and bainite phase, right? And where our bainite is pushed forward, right? And these are sort of referred to as bays. So in this case, we can get down, we'll talk about Austempering, where we come down here, quickly quench to some temperature above the martensite start, and then come in to get a lower bainite temperature, right? And then we can also have basically where we don't see a bainite bay, where we have a pearlite and then a large gap between the lower end of this TTT curve and the martensite start. Or basically we can have ones without a pearlitic bay, right, where we need a significant degree of undercooling before we have anything happen. And then the kinetics of it are such that either we get a fully bainitic or fully martensitic structure with very little pearlite formation, right? And so these are sort of the classes, right? And depending on what alloying elements we have, we're going to move into these different regimes, right? And so what we're talking about here is a little different than austenite stabilizer and martensite stabilizers. I mean, austenite and ferrite stabilizers, because there we're talking about equilibrium phase, right? What is going to form? Here in the TTT diagram, we're talking about kinetics, right? So this is what phases can we reach in a finite amount of time, right? And that's different than what if we hold it for an infinitely long time, what phases are going to show up. Right? And so this is all about how the different alloying elements move the TTT curves, right? Not necessarily what the final thermodynamically stable structure is, right? We may never be able to, right? Remember, graphite is the thermodynamically stable carbon phase, but for virtually all steel alloys of interest, we have cementite, right? It's all about the kinetics. So all of the alloying elements, with the exception of aluminum, cobalt, and silicon, technically increase the stability of the supercooled austenite, right? So that means we push these curves. If we're stabilizing the austenite, right, it's going to take longer to transform. So these curves get pushed to the right. Right, so we have to hold for a longer time before we develop our austenite, right? And then we have a whole host of elements, right? This nickel, manganese, right? All these rare earths, copper, zirconium, and gold, right? And so these, oops, go back to the TTT curve here. right? These stabilize the austenite, right, and move the TTT curves, shift them down to lower temperatures, right? Austenite, then we have a, oops, wrong way, right? A set of ferrite stabilizing elements, right? And these are the BCC type, right? So they tend to move these curves up to a higher temperature, right? And then aluminum, cobalt, and silicon are the oddballs, and they move this to the left, right? So based on what regions of the phase diagram you're looking to get, you can alter your alloying chemistry to be able to alter the rate at which the various phases are going to form, right? So you can adjust your heat treatment then to get what you want. So it's a combination of alloying elements and the heat treatment schedule, right? Alloying elements are going to shift what phases are there and the kinetics of how to get them. And then your heat treat schedule, you decide on how you're going to get to actually get to what you want. Yeah.
Does that top A horizontal line indicate that it's starting to form pro-eutectic or eutectoid ferrite?
No, that's the full austenite phase field. You go high enough there, then your austenite is now thermodynamically stable, right? You're never going to form ferrite, right? Okay. So the effect of the alloying elements is less pronounced in the bainitic region. You have to do more with your alloying to try and shift the bainite region, but they follow the same trends, right? But your diffusive, which makes sense, your diffusive transformation is going to be more sensitive. The rates of your diffusive transformation can be more sensitive to the composition than the rates of your displacive transformations, right? Grain size also has an effect, right? So the finer your austenite grain size, the faster your transformations, right? And that's, again, largely a function of nucleation, right? More grain, smaller grain size, more grain boundary area, easier to nucleate, right? And if you have heterogeneous austenite structure, right? If you have a nice uniform grain size versus one that you have a wide distribution of grain sizes, what do you think is going to happen to the curve? For heterogeneous, or for heterogeneous, it's actually going to widen, right? If you were homogeneously small, right, you're going to shift, right? So the more heterogeneous your structure, right, you're going to have regions that transform quickly and regions that transform slowly, right? So for the mean grain size, comparatively, right, you're going to have a slightly wider, right? Slightly wider. Okay, so now we're going to move into sort of actual heat treatment schedules, and so a common one is tempering, right? And basically, the idea here is we want to quench quickly, miss the nose of the TTT curve, right? Miss the ferrite curve, come down some temperature above martensite start, so we're not going to form martensite, right? And hold until we have a structure that's basically 100% lower bainite, then cool down through the martensite, right? So the end of this is that we have a fully a structure that contains fully lower bainite, and this is often given to high carbon steels and low alloy steels. And the idea is we now have a single heat treatment process that give us hardness and strength that's comparable to hardened and then tempered martensite, right? Remember, lower bainite actually has a higher toughness and higher strength than upper bainite, right? So that's why we want to do it, because the lower bainite has the carbides within the laths, right? So that gives us additional strength. And then because the carbides are more uniformly dispersed, we don't have so many in between the sheaves. That gives us a bit of a boost in toughness, right? The problem is, depending on how flat this curves out near the martensite start, you may have to hold for long times, right? So you really need to be able to. It only is feasible in alloys that either have a distinct bainite bay, right, or that this curvature is not so great. Okay. So then another important heat treatment that doesn't involve martensite is what's called patenting. And this is actually the way of making the highest strength commercial steel, right? And it's used for cold drawn wire, so piano wire, springs, braided steel rope, right? This typically goes through this patenting process. And so you come through the furnace, you go fully austenite, you cool down, and you run through the wire is slowly drawn through a controlled bath. Historically, it was done with lead. Now they use other molten lead. Now they use other metals. But you run it slowly through this bath and hold it right at the nose of the TTT curve, right? So the idea here is, remember, the further forward you are, right now we've got lots of nucleation of pearlite. So we end up with a very fine pearlite structure, right? And with no martensite, right? And we can actually get strengths that approach 5 gigapascals and still have 20% ductility, right? But it only works for very uniform, thin cross sections, right? You can't do this for any kind of bulk piece. It works, again, really well for wires. Right? Yeah.
Why? Why is it that strong?
Because you've got such a fine pearlite structure, right? So think about it. You've got a really, really fine pearlite. You've got a very fine dispersion of the cementite, and you also have dislocation-free ferrite that can still give you the ductility.
Okay, so it's taking like super advantage of all pitch, essentially.
Basically, yeah. Right. I mean, right. You've got huge obstacles, but you've got very confined fine pearlite plates, right? And you're making sure you're hitting it right where you have the most nucleation of the ferrite, right? So you've got very fine regions. right? So it's a pretty cool process. So if we then go into structures that have austenite, right? We have bulk heat treatments, and then we have surface hardening processes, right? Full annealing we talked about before, right? And the idea is we heat above A3 for hypoeutectoids or A1 for hypereutectoid, furnace cool, and we get coarse perlite, and this has a very low hardness and a high ductility, right? This is sort of a long time. We want to make sure if we're hypereutectoid that we don't go above this line here, because then we get proeutectoid cementite that forms along the grain boundaries, and that gives us crack propagation, right? So recrystallization annealing is very similar, except now we have cold work grains, right? And we're going to heat slightly below the A1 line here, right? Slightly below our eutectoid temperature. And since everything's cold work, now we anneal and we get stress-free ferrite grains, and we use this in between processing steps, right? Where if we're rolling, our steel gets work hardens, right? And so to keep working it into whatever we need to do, we need to soften it, right? And we don't want to grow large grains. We don't want to go back to the austenite structure. So if we have cold work in there, we can recrystallize. Right. Stress relief annealing is basically the same thing, except we don't recrystallize, we just recover, right? So we want to annihilate our dislocations and polygonize our structure. And then the last, right, we basically have spheritization, right? The idea here is we want to start with our perlite structure, right? There's a lot of interface here, right? So just like grain growth, we can reduce our interfacial, there's a natural driving force to reduce the interfacial energy, right? And our carbides will spheritize, minimizing the surface area, right? And this is done to make things easier to machine, right? And this is done pretty much just for alloy steels or high carbon steels, because right when we need to, these systems are hard, and so when we need to be able to machine them, they're typically given a spheritization treatment first, right, machined into shape, and then reheat treated to get the final microstructure they want. Low carbon steels aren't normally spheritized because it makes them too soft, right? It makes them hard to machine. Yeah.
When you spheritize, you can heat treat afterward and get back any kind of perlite structure.
Yeah, so if you just go above right back into your austenite phase field, the cementite's going to dissolve.
Yeah.
Right? Your carbides will dissolve, and then you go through whatever schedule you want.
So generally pieces like this, they're just machined for practical.
Yeah, it's just spheritization heat treatments are usually just so I have a block of metal, I need to be able to machine it into my final shape. Yeah, right. Trying to machine it in the purely perlitic state, it's too hard, right? Too difficult. And then the final is diffusion annealing, which you take it well above all the critical points tie into the austenite field, right, and hold at prolonged time to homogenize the composition of the material, right? So if you have a cast ingot where you have significant solute segregation, you would go through a diffusion heat treatment to bring everything together, right? And then we talked about normalizing, right, a little bit before, right? The normalization is we austenite, then we air cool, and we want a fine perlite with higher hardness, right? So as opposed to annealing, we want low hardness, lower tensile strength, and high toughness. In a normalized state, we're trying to impart more hardness with the understanding that there'll be a reduction of toughness, right? So we end up with a coarse perlite structure in the annealed state, a fine perlite in the normalized state that's often hard to see with the optical microscope, right? In a full annealed state, we've basically reduced most of our residual stresses. Our internal residual stresses can still remain in the normalized state. Okay, so now on to hardening and tempering, right? So basically here, we're going to follow a path. Again, we're going to try and miss the curve, the front of the TTT curve, come down through the martensite start into below the martensite finish. So now we have a fully martensitic structure. Hold for some time just in case there's a little bit of isothermal martensite that grows. Come back up, right? We don't go too near the critical temperature. We don't want to austenitize anything, but we want to come back up in temperature, temper, and allow for diffusion of the carbon to form carbides and give us some ductility back, right? And so the critical thing is going to be the quench rate. Yeah.
Wait, I thought we said that forming carbides would lead to like low ductility since they're nucleation sites for cracks.
But the martensite itself is there's stages of the tempering, right? We're also going to go from BCT back to when the carbon diffuses out, go to BCC, right? So we have the BCT structure itself has no ductility, right? We can't move any dislocation. It's very difficult to move any dislocations through the tetragonal structure. The pyro stresses are just too high, right? So it's this balancing game, right? And so alloy steels tend to be less critical with the cooling rate, right? Because a lot of times there we need to worry about how fast our solute atoms can diffuse, right? So we can a lot of alloy steels will form martensite on air cooling, right? High carbon steels typically are oil quenched, right, to get the critical cooling rate to miss the front of this curve. Medium carbon steels need either water or brine, either dunk or spray quenching, and low carbon steels, there's basically no way you can cool fast enough. You're always going to come through, right? You're not going to be able to get a fully martensitic structure.
You'll get some martensite after the nose, though.
You'll get some martensite, but you won't be able to get a fully martensitic structure. Right? Because the driving force for martensite formation is smaller because you have less carbon, so you have less distortion in the ferrite lattice. Okay. So there's a lot of stuff that goes into the hardening process, and we're not going to have time to talk about a good chunk of it. But really the composition is part of it, but it's also the size and shape. You have a big piece, right? outside is going to cool at a very different rate than the inside, right? You probably saw this if you're in the metals lab, you saw this in your geometry bars, right? That the towards the edges has a different structure than towards the center of the bars, right? But also the grain size of the austenite, what you quench, the surface conditions, all of these play into the hardening, and then the exact quenching methods play a huge role. Normally, what we think of is sort of what's called mar tempering, right? And a way of trying to get a uniform as structure as possible is you cool down and try and miss the nose, hold it above the martensite start temperature until the temperature within your part becomes uniform, right? So you don't have a big gradient between your surface and your interior. Then go down through martensite start to martensite finish, and then temper, right? And again, the key is you need to be able to miss the nose of the TTT curve and the bainite bay, right, if there is one. And then, so as we've mentioned, if you can't quite miss everything, or you can't cool below the martensite finish temperature, right? So some alloys, martensite finish is lower than room temperature, right? So if you can't actually get there, we're going to have retained austenite, right? So some cases you want retained austenite, other cases you don't, right? You have increased ductility, right? You have increased formability. You can strengthen or straighten after processing operations, and then basically you have a much lower distortion on quenching than steels that don't have retained austenite, right? The disadvantages is soft austenite decreases the hardness, right? And depending on the service condition, you may transform to lower bainite, right? Which means if it happens in service, either a bainite transformation or a martensite transformation in service is going to distort your part, and you won't have dimensional stability in service, right? Which, remember when we talked about aluminum casting going through phase transformations, right? That gives you large residual stresses because your part is typically confined in some assembly, right? And so that can cause you big problems. And remember, the austenite phase isn't ferromagnetic, right? So if you need magnetic properties, you need to make sure. So for steels that have martensite finish temperatures below the below room temperature, they're given what's called sub-zero treatment. So basically, what you now have is you come down to room temperature, and now you've got this bath here, and this bath is filled with some sort of organic solvent that's cooled by liquid nitrogen, right? Basically, you have liquid nitrogen going through a pump, and it's spraying. So now you've got very cold nitrogen vapor cooling this bath that you then run your steel through, right? And this pretty much, depending on what your coolant is, your quenching medium is, you can then get below your martensite finish temperature, right? So this is sort of expensive, right? And typically, we don't quench with liquid nitrogen directly, right? Because it's never actually in contact with the surface. Right here, we've got a nice liquid quenching medium that we're in contact with that doesn't boil off, right? If you just quench hot steel or warm steel directly with liquid nitrogen, right, you get the Leidenfrost effect. You got a layer of vapor, and you don't cool fast enough. It's not efficient. You get slow quench rates, and you waste a lot of liquid nitrogen, right? Okay, so now we're fully hard. We got full martensite. Yeah.
I have a question about the martensite.
Yeah, so tempering is the whole next 10 slides.
Oh.
Right, this is what, yeah. So we're going to basically spend the rest of the class on tempering and properties of tempered martensite. And then next, on Monday, is all the surface treatment stuff. Right? Okay, so fully hardened steel is not particularly useful, right? It's way too brittle, right? You have no ductility, right? So then we have catastrophic failure, right? We don't want bridges to shatter. We want them to bend, right? And also, you have exceptionally high internal stresses. Remember, the martensite formation has a very large shear component. You got 20% shear, and in some cases almost 10% normal component. So you've got potentially 30% strain that's accommodated through the formation of the martensite, right? So you've got very high residual stresses in your material, right? This is the fully hardened state, and over here is sort of a tempering temperature, right? And so even if we have retained austenite in there, right? If we didn't go completely to martensite, we still have a lot of the same problems, but we have a little bit more ductility in this case. But both of the martensite and the retained austenite are metastable, right? So depending on the service condition, they can change, right? It's okay if you're going to keep your steel at the Arctic, right? But if you're in the tropics, right, depending on what exactly you are, or what your in-service conditions are, you can these phases can revert to the stable ferrite and cementite, right? And so tempering is not just about the getting a little ductility back, right? It's also making sure that you're at a stable structure. Okay, so then basically what we do is we want to heat below our A1 temperature, so heat back below our eutectoid temperature, hold, and then cool slowly, right? So we don't have any gradients that appear, right? And we exhibit the classic trade-off that as we temper, our toughness and ductility go up, but our hardness and strength decrease. So we sort of want to find the happy medium where we have sufficient ductility for our purposes, but we haven't traded away too much of our strength. Okay. So, oops. So basically, as we hold, carbon is going to be rejected. Why is this font small? Just like, okay, sorry, I didn't realize. Carbon becomes rejected from the martensite lath to form carbides. That's the word I'm looking for. Carbides. It's right there. Right. And now our microstructure, we basically have martensite with our substitutional solute, carbides, and some retained austenite, if any. Right. So remember, we're at a lower temperature source. Our substitutional solutes are going to partition are going to partition very slowly. There's no crystallographic orientation change associated with the tempered martensite. Right? We're not changing our grain, our orientation at all. We're dissolving out. That we're moving out the carbon. We're going to BCC ferrite. Right? And then we also have to consider that as we quench, we may have what's called auto-tempering going on, which is segregation of the carbon to form the carbides during our quench through the martensite region. So depending on how fast we can quench, we have movement of the carbon, right? It's difficult to keep carbon in place, being that it's an interstitial. So we have a couple stages of tempering. So basically in what we call tempering stage 1, right, medium and high carbon steels, the interstitials have mobility can diffuse at room temperature, right? It's hard to keep the interstitials in place. If we go up to about 250 C, we form HCP epsilon carbides, right? And that basically forms fine laths on the 001 planes of the martensite, right? So we have a good lattice match, right? We get refined precipitation, right? Basically, we now have an age hardening that occurs, right? So at the end of stage 1, our martensite is still tetragonal, right? But we've perhaps, depending on the system, we've perhaps actually hardened it a little bit by giving us this nice refined precipitate structure. If our carbon concentration is too low, we won't form this epsilon carbide, right? And if our carbon concentration is too low, it's hard to get a fully martensitic structure in the first place. So tempering in stage 2 are tetragonal austenite decomposes, right? Basically to bainitic BCC ferrite and cementite, right? And right, so that's stage 2. So first stage, we grow carbide, epsilon carbide, but we're still tetragonal. In stage 2, we go from tetragonal to BCC. Right. In stage 3 tempering, right, we are ferrite, and depending on the temperature, we may have missed the bainite transformation before, and if that's the case, now we grow as Widmanstatten ferrites. And so at these temperatures, in this stage 3, the nucleation sites for this is going to be our epsilon carbide array that we formed, and then they're going to dissolve, right? We can also nucleate our Widmanstatten plates from the twins in the martensite, right? We have twin martensite at higher carbon concentrations, or the grain boundaries, right? And then we tend to end up with sort of spherical cementite regions, right? So here we see nucleation of the Widmanstatten, which gives us ferrite cementite along our twin boundaries in the martensite. So this is a twinned martensite structure, and now we have cementite along the twins. Along the grain boundaries, you sort of have these ellipsoidal or spherical cementite that forms. Right? And then stage 4 tempering, if we go up to even higher temperatures, right? So before we were, stage 1 was below 250. Stage 2 is up to, stage 2 is below, 250 to 300. Stage 3 is above 300. And then stage 4 is above that up to about 800. And at this range, we get spheritization. Right? And so this is sort of the important graph. There's a whole lot. I don't want to spend lectures on the actual mechanisms of what's going on here, right? But it's just the same nucleation and growth that we talked about for each of the different phases. But oops. So you can see all the changes and the hardness with respect to the tempering, right? If we get too high above 600, we get recrystallization and very coarse ferrite. In the intermediate temperatures of 300 or so, we start to get recovery and spheritization of ferrite. At lower temperatures, we get our epsilon carbon and our fine dispersion. So we can actually, depending on our composition, increase our hardness because of the fine epsilon carbide, right? This becomes really pronounced in alloy steels, and we call it secondary hardening. So basically, just the properties, right? And they show the same trend as what we see on the other chart. Right? Decrease in strength, increase in toughness, and there's a carbon composition dependence on how much they go, but they all follow the same trend. Okay, in alloy steels, things get complicated, right? Most of our elements shift remember our TTT curve shifts. When we're quenching, we're not holding at a constant temperature. So we need to think about our CCT curve, where our quench line comes down through our TTT diagram, right? And so alloying elements shift to longer times, which is good because that allows us to miss the nose with our quenching. But they can also lower the martensite start and martensite finish temperatures, which in alloy steels tends to give us a larger amount of retained austenite. Right? And so, and some alloys, some elements are going to are not easy carbide formers and are going to stay in the ferrite as solid solution, right? Others are good carbide formers are going to tend to partition to the cementite or the carbides during the tempering, right? And so if we see these with the presence of carbide formers, we see a very significant amount of secondary hardening that goes on because of forming these fine dispersions of the carbides, right? So, right, we can, depending on the system, we get in molybdenum, we get a softening. Then as the carbides form, we get a hardening again because of the dispersion. Right. sometimes this is called red hardness, right? And it's called red hardness. This happens in high-speed tool steels, right? And it's sort of important because as we're machining something, you're generating a lot of frictional heat. So in tool steels and high-speed steels, they were developed and they were instantly replaced the high carbon steels for machining applications because they actually become harder even as they get red hot. Right? So if you're sharpening tools, right, you need to grind tools to sharpen them, right? And you've got a huge amount of friction at the grinding wheel. You don't anneal your steel, right? You don't make it softer by sharpening it, right? And you maintain hardness as you're machining it, right? And it's essentially just in the age hardening process. It's the same story that we talked about with aluminum, except now we've got these fine carbides, dispersions, vanadium, molybdenum, tungsten carbides, right? Chromium steels at high chromium concentration, right? And so the amount that we're going to get is directly proportional to how much of the carbide forming element we have and how much volume fraction we can actually turn into to carbon. Other elements tend to stabilize this, right? So silicon stabilizes the epsilon carbide. Nickel gives us nice solid solution strengthening, but it's not a carbide former, right? Manganese resists coarsening, so that's good to have in there because that allows us to keep a fine dispersion at higher temperatures, right? We don't coarsen our carbides. In alloy steels, right, in plain carbon steels, we said martensite loses its tetragonality by 300 degrees, right? But in if the steels have our chromium, tungsten, molybdenum, titanium, vanadium, silicon, high carbide formers, we can actually retain the tetragonality up to 500 degrees C. So we have sort of different temperature ranges, right? And we can see the effect of the different alloying compositions has on the strength as a function of tempering temperature, right? And so, you know, vanadium, right, with a little molybdenum in there, right? You can see how our right, if we start with just iron nickel, and then we add some carbon, we add some chromium, we add cobalt, molybdenum, and that's 5, not a B, I'm sorry. Right, and then add some molybdenum, we can see we get really drastic changes in high temperature properties with respect to the alloy composition.